Hmm. So this is okay. So I was gonna say this is a test, but it's not a test anymore. I was just testing the headphones with the mic because with the microphone because I forgot mine, and this is sort of a replacement one. Okay. Anyway, so this is where we're left with the controlled the controlled IX and control and the Margalose. So that has a name, the Margalose gate. Interesting. The Margalose gate. The Margalose. 2003. That's interesting. The Margalose gate. So I kind of thought, like, I think I did like a pretty long video just on that, and I realized it's all the same technique, and even these is one of the things that I'm learning out of that is really this to use this duality of the dimensions, and the fact that you've got dimensions within the Hilbert space that are orthogonal, and so you can I think that definitely I think that allows you to do these types of things because you're basically I'm lacking really the technical words to explain that, but what I mean is you can work on one dimension like the so if your target dimension is the x, right, because that's what you want to do is like an x, it's like a bit flip, so you want to rotate the target on the x, but you can use any like another dimension to do these partial rotations, and in this case here it's using the z dimension. Here this is on the z, and here it's on the y. And actually I was thinking about a way to show how this really works. It's the same technique really, and I kind of feel like a neat way to do that is with Qiskit, because I'm learning now all the different visualizations you can do with Qiskit, and it seems pretty powerful in terms of for that particular case, for the block sphere. With Quirk, I would say can try, but I think the block spheres are a little bit too small, but we could try if I zoom in. So if I zoom in and I exactly, so and we'll take a look at the block sphere here, the one at the target. So rotation y pi divided by 4. So I think for this I have to use. Okay, so this is just these. Okay, so pay attention to these blocks here. So look that it's rotated like a quarter, right? Because if this would be these, then we've rotated half the way across the so it's the y-axis that's rotating. So pay attention that at the end of the day, the target, like the fact that we're going to end up down here where it's the representation of 1, is shared between the two axes. So in this case, what we're doing is we're approximating, we're getting close to the target operation by doing step by step. And so the strategy here is you do a first rotation, then you apply a control knot based on just like one of the 2 qubits, right? So and these, so the trick here is if you'd have more than 2 controls, then you'd have to change that 1/4. That wouldn't work anymore. So you have to have probably 1/8, probably if you have 3 controls, for example. But the technique is the same. So what's happened now? So now that we've got a 1 here, it's basically, I mean, it has basically mirrored that. So it's basically has gone from that point to the opposite one. So now we are missing a 4th. We're literally missing a 4th rotation, like 1/4 of the rotation to get to the final state. And so that's what you're kind of doing with the next, is completing it, right? So you're assuming that here we've got a 1. So I'm gonna do another y. So now, in theory, we're done, right? Now pay attention, it's not optimal because we do have a sort of a leftover phase. But that's the point here, is that those algorithms don't correct these phases at the end. So, in exchange of that, you are a bit more efficient. So let me see. Okay, so now the thing here is, if this will be the input, like, we want to correct that, right? Because we've gone all the way, but we shouldn't have, because we don't have a 1-1. So that's why this is going to act as a correction. No, sorry, this is not going to act as a correction. So nothing happens here, but we're repeating the same, but rotating backwards. Yeah. So you're basically having a. So I wanted to do it with Qiskit, but it just takes too much to set it up. And I see that's kind of good enough. So we are kind of. So with this, you're going back. If I put a block sphere here, so now you're kind of undoing that. You're going back up, and then you're going back. Now, the beauty of this is that if there's another one in here, right, we've engineered, so this is set up in such a way that this one has, so this particular control knot, it's been applied, so we're back at square one, but now this portion that's used, that used to be the last 3 gates that are used to be a correction for the other case, now also correct us to actually apply that control knot again. So that's the same, but on the other side. So it does a fourth this way, then back down, and then we're here. So it's the same. It's pretty. It's the strategy is you're approaching your target operation step by step, and you're controlling and doing and undoing, and that's, I think, a general strategy for all this kind of stuff. So I'm gonna leave it here. That's definitely an interesting case. So pay attention that with 0, 0, nothing will happen here. So basically, none of these control nodes will activate. So those things just kind of correct themselves. If I would have a 1 in here, right? Basically, what would happen? That's an indicator. So here you do a fourth. Here you do another fourth of rotation. So you're basically half the way. Now that control doesn't do anything because it's an X rotation, but you're along the X-axis, and so the rest just again corrects itself. So it's about balancing corrections and uncorrections. So that's kind of the trick used in here. Okay, cool. Having said that, let's move on. Let's move on. Let me clean that up. So the next step was to understand why there's a need to introduce a Toffoli gate with a built-in swap. A Toffoli gate implementation with a minimal 6 control X gates requires 3 qubits interconnected in a triangle. Recent a Toffoli gate, okay, with a minimal 6 control X gates requires 3 qubits interconnected in a triangle. Recent IBM Q devices, after IBM Tokyo, do not have a structure that can embed triangles. To deal with this situation, we propose a Toffoli circuit suitable for a one-dimensional layout, as shown in Figure 10. Where's Figure 10? Figure 12. Oh, no, I mean, Figure 10 is the actual circuit. Okay. By adding the CX gate surrounded by a broken line to the general Toffoli gate, the composition swap is built in, and the circuit can be performed with qubits connected in a straight line. Okay, so the point here is, so if this is, so let's say this is qubit 0, this is qubit 1, this is qubit 2. So if I take a look at how these things are connected in here, it's basically, here you've got 0 to 1, here you've got 1 to 2. Here you've got again 0 to 1. Here you stay kind of like 1 to 2, but it's like bidirectional. So far we've only got kind of a general connect. Yeah, but still now you're connecting. You're connecting. I probably need to see the optimal. So what's the 6? I'd like to know what's the 6 control X gate implementation. Oh, that should stay. Why does it float with me? Because now we've got a connection between 0, 1, 1, 2. But now you do have here, that's confusing. So this is between 2 and 0. So that's the triangle, right? So it's 0, 1, 2, and that's the triangle. 0, 1, 2, exactly. Okay, so but I see the trick. But if we add a what's the Toffoli gate optimal circuit? Is it? One, two, three, four, five. No, that's not. Toffoli gate decomposition. I think I've seen that in the. Oh yeah, that's it. Okay, that's this. Is this? Is it this? Yeah. So we've got 1, 2, 3, 4, 5, 6 control X gates. Seems to be like that. And here you've got connectivity between 1 and 2. Yeah. 1 and 2. Okay. So 1 and 2, 0 and 2. So that literally means sorry. I cannot have here can I have that exactly? So it seems 2 is in the middle in this case. It seems, yeah, so this is between 0 and 2 and 1 and 2. So this is this. This is another one between 1 and 2. This is between 0 and 2. And now we have 0 and 1, 0 and 1. Okay. Yeah, so we got the triangle. Okay, so I get it. So the way to break that is if you add this swap in here, it's effectively as if you would be swapping the wires. So this means that that these two controls belong to now Q1. So between Q1, okay, belong now to Q1 to the qubit 1. So it's a connection between qubit 1 and qubit 0. So it's this one we already have in here. Now the swap is between 1 and 2, so we already have that connection, and so this one is not needed anymore. Yeah, okay, neat. That's a neat tree. Okay, I get it. That's an interesting trick, I guess. So the only thing is that then you have to know that it's the same as a Toffoli gate and a swap. So probably what you want to do is after you're done with that, you want to correct that swap again. Yeah, it's nice. Okay, so let's close this. So so I understand why this is needed. Now, the circuit requires one additional control. So okay, so you're adding one more. You're adding more control NOT gates though. So you're increasing the chances of error, but in turn you're having a you can actually implement it at all. I mean, because you wouldn't otherwise. Okay, so circuit has one additional control, the minimum overhead. However, since swap is built in, it is necessary to consider the location of qubits in the output state. Swap is built in. By using those components, we can configure a control like an N control X gate for recent IBM Q devices using 6 times N minus 5 control X gates. It is known that the N controlled X gate can consist of 2 times N minus 3 Toffoli gates with N minus 2 ancillary qubits initialized to 0. A Toffoli gate contains at least, because our target is to build like an N controlled, an N controlled. Like if we're having like if our Grover algorithm is on like 4 qubits or 3 qubits, we need like a 3 control X gate for that for the amplitude amplification. By using those components, we can figure. Okay. So this is how you build a. It is not okay. A Toffoli gate contains at least 6 gates, 6 CX gates, 6 control NOT gates, as shown in Figure 11. Toffoli gates can be replaced with RTOF except for the central one. To support additional implementations, we show the procedure of implementing to support additional implementations. Okay, for the reproducibility. Okay, so that's that's nice. Okay, so I'll use that because at the end of the day, what I will do is I will try to build that on using Qiskit and kind of reproduce the experiments that they do here, right? Now I don't have any kind of or any sort of premium access to or whatever, so I don't know. I've never used a real machine from the IBM Q experience, so I will. Let's see what I'll get. Okay, so data qubits. An N-controlled X gate implementation. Input N plus 1 data qubits. Okay, first let me take a look at these. So, but don't these phases somehow, shouldn't you correct those phases? First of all, okay, so it doesn't matter which one you use. But if I now, I want to try that. So if I now say, okay, I got these. I want to pack all that, make a gate from all the circuit, and I'll call these the how's it called here? The RTOF M. So RTOF M with a gate. So if I clear the circuit and I use an RTOF M, that is basically that's basically working like that, right? But the cool thing here is it seems that doesn't add the phase. So I will let's try with this one. That's the one that lets the phase. Let's see if that affects anyhow the overall composition of the N control X gate, because that's what's interesting, because this one doesn't seem to add. So the point here is it doesn't add any nasty phase that we need to correct. Okay, but let's try this. So okay, so this is basically HT. Okay, so this is a Hadamard and a T, and then we've got like, okay, so a control NOT minus D. Then we've got another control NOT in here. Then we've got T, another control NOT in between. And I think we're almost done, right? Polymark gate that behaves like it should, right? So if I put our cell, if I put this into a plus plus, now, oh, yes, now. Okay, so the only problem is that it does add this 90 degrees phase here. But let's see, let's make a gate out of this and let's call it the RTOF IX. Clear circuit, and let me bookmark this. I'll call it RTOFs. I know I have those things kind of saved in here. And what I wanted to do is I wanted to basically now implement, using those gates, this in here. Okay, so so you can do this implementation by adding these ancilla qubits in between. This means these qubits, like the A0, it's not supposed to be anyhow a control, but it's just used to chain the Toffoli gates. So yeah, so then you're basically saying, you know, if these and these are 1, and this is 1, and so on and so forth, right? So you're using these ancilla qubits to chain those things, to chain the condition, to chain the different gates. Okay, so let's try to, I don't know, let's do with the RTOF X, and let's see. So you would chain them this way, right? And now you would basically do, why do you need to uncompute though? To free the ancillary qubits. Toffoli gates and the unclosed dashbox can be replaced with the relative phase gates. Toffoli gates other than the one enclosed in the hashed box can be replaced with the relative phase gates. Thereby, the number of phases can be reduced. Yeah. Now here we would do a normal Toffoli gate with a swap, right? Because that's what we can do with that processor. And then, okay, so but if I have, okay, so for me to understand, let me put density chance. No, I think I wanted to have, that's the target qubit here, right? So that doesn't go on, 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 doesn't go on. Now it goes on. Now in theory, this here I shouldn't care. So these are ancilla qubits, and they can all be 0. It's funny because it's funny that it works regardless of whether they are 0 or not. And these can be 0 as well. Yeah, that works. No, the target is this one. Yeah, right? The target is this one. I mean, that's where the target is. So I think this is a, so that's kind of a question here. So is the target really here? The target should be these, right? Now, I don't know why the uncomputation is needed. I don't know if it's just to release the ancilla qubits, I guess. Yeah, I guess so, because I mean, otherwise, I don't really know. Do we really need to uncompute? That's an interesting question. Do we need to uncompute? If I would now want to use the other qubits, like, I don't know, say, I need to zoom out, I think. Sorry, here. So if I if I know where to do something like that, I mean, I don't know why. Do I really need to uncompute? That's the question. So if I don't care about the ancillary qubits, you still, yeah, I don't know. So that's kind of one question. Do I need to really uncompute? And because it seems to work, we can then. So whenever I will do, I think in one or two videos. So actually, probably the next video, I'm gonna build that whole thing in Qiskit, and I'm not gonna use their code. I'm gonna because I think they've got a repository with the code. I'll just do it from scratch and then kind of compare and see if I can do that without uncomputing, because it seems to work, assuming that's target qubit, right? Okay, and I should probably put all my feedback into finally into a Google Docs to share. I mean, and compute doesn't hurt, right? If I kind of apply these gates again. Now, it's quite interesting to see that for some reason, oh yeah, there is still a phase. Okay, there is. It's a minus 90-degree phase. So that works as well. If I change the RTOF fix gates for RTOF M gates, what happens? So if I do these, okay, then this doesn't add the phase. Okay, fair enough. Okay, perfect. But I'm still not clear whether the uncomputation here is needed or not. So that's kind of a question mark. Yeah, and so what else? I mean, I think we're kind of ready to go ahead and implement, which I'm going to leave for the next video. But basically, so this is an algorithm to implement that. Okay, so RTOF and then 4K RTOF. Okay, so this is just the high level, like a pseudocode for basically implementing the that in here. Now, question here. So, actually, another question: why do we need an actual? Why do you need that at the end? Why cannot not this be another RTOF gate? Why does it have to be why does it have to be the actual Toffoli gate? And like if I if I use this component, I can use gates. It is now that if say I use if I use a another RTOF M in here, I mean, that's on, right? If I turn any of those off, then that's off, 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 off. But look at this. So if I put a 1 in here, then that turns off. Whereas with Toffoli gate, that would be off as well. Okay, sorry. I think the comment I made before is just crap. But I mean, just with RTOF M's seems to work as well. So those need to be initialized 0. And then that qubit is on. And if I turn any of those off, then so why do you need that? I mean, that's even more efficient because you've got less control NOT gates. Why does the last one need to be, so this is only one dimensional, it's equal, like 1, 2, 3, also enter a gate. Maybe I missed something somewhere. So we also introduced Duffel gate with built-in solver. Duffel gate implementation with minimal 6 CX gates across 3 cubes interconnected. Recent MBNK devices do not have a structure that triangles the situation was a Duffel circuit suitable for a one-dimensional layout. I mean, those layouts just need like, they just need like also like a linear interconnection, right? Because it's 0 to 2, 1 to 2. That's it. They can also be implemented in these architectures. By using those components, we can figure out, okay, so that's really not clear to me. One additional control X gates, the minimum overhead. How is this sub is built in? It's necessary to consider the location of the qubits. There doesn't seem to be a motivation for that either, or at least I can't find it. I can't find it. Seems to work this way as well. Okay, anyway, so that's another open question. That's another open question. And then we've got basically, if the processor can embed the structure shown in figure 12, the procedure can be executed without additional steps. Figure 12. What is figure 12 here? No, but still, I mean, why? Okay, that swap is a correction. Okay, yeah. So sorry, this is the, okay, so that swap is a correction of that. So, but still, that doesn't seem to be it's needed. Qubit connections for algorithm 1 data and instead of qubits are denoted by, okay, maybe I'm just missing something. Okay, and then the next is already experimenting on IBM devices. We evaluated our proposed algorithm for finding max count for K13, K14 on current processes. If a given graph is K14, our algorithm requires 5 physical qubits, 4 data, 1 ancillary, and 1 virtual qubit. Figure 13 illustrates the correspondence between the given graphs and qubits. Okay, so that's going to be the next video. I'm going to implement that and run the same experiment and see what happens. Implement it with Qiskit. Now, I still got the following open questions. So number one is why like what's the reasoning behind why do you need the last one to be an actual to be implemented this way? Seems like, is it because you want to correct the is it because you must correct the phase? Maybe that's why. Maybe the reasoning behind this is that you want to correct. Okay, so you want to correct the phase once. Okay, I get it. So you with these you're piling up a phase, and then you must correct that phase once. And so if you correct it at the very end, applying these gates, maybe that's the reason. Because you at the end you want to have the phase corrected, but you only want to do the correction once. So you don't want to have to do the correction for every single little piece of your N control X gate. So you want to have one last gate here that actually corrects the phase. Okay, so that can be a reason. I'll ask. And then, do we really need to uncompute, or is it just standard practice because of the ancillary qubits? Yeah, I think that's about it. Perfect. I think I'm ready to implement that. That's cool. That's cool. Cool. Let's see how that works though, with the putting all the pieces together. Nice.